Hello, thank you, Benjamin, for the introduction. So, yes, precisely, I'm going to. So first, I'll recall a bit what we did yesterday, just orally, and then I'll explain. Yes, I'll present a case in which yesterday's theory does not apply, even though it's linear with constant coefficients and so on. And because it's precisely a degenerate case, and that was the red part in the theorem, the red assumption that I highlighted yesterday. And then I'll also explain how you can extend that theory to the case of rough boundaries. Okay. So yesterday I told you. So first, if you recall, I told you that boundary layers were ubiquitous in ocean models, and I told you about two different kinds of boundary layers that played an important role in the general oceanic circulation: the Ekman layers and the western boundary currents. So yesterday I told you how Ekman layers were constructed by balancing the high rotation with the viscous dissipation. And today, actually, I'm going to focus on the other kind of boundary layer. So today's talk will be entirely centered around one model, which I will call the Sverdrup model. And which is as follows. So it is dx psi epsilon minus epsilon by Laplacian of psi epsilon equals some source term f in a domain, so for the time being, I'm just denoting it by omega. So omega is a domain in R2. It's smooth and simply connected. Unbounded. I'll explain a bit what everything is here. And I'm endowing this PDE with two boundary conditions on the boundary of omega. And these two boundary conditions are as follows. So I'm assuming that psi epsilon vanishes, as well as its normal derivative on the boundary of omega. Okay, so it's easy to prove that for any epsilon and f, say in L2, this PDE has a unique solution, just a consequence of the Lax-Milgram lemma, for instance. Okay, and the purpose is to study the behavior of solutions as epsilon goes to 0. Okay. So just a little bit of modelization. I'm not going to do the whole derivation of this equation today. Yes? Equals 0. Thank you. I'm not going to do the whole derivation of this equation today because unfortunately I don't have time. But I'll just explain a bit. So psi epsilon here is the stream function. Which means that the velocity of currents is a two-dimensional velocity. So the velocity u epsilon is the gradient perp of psi epsilon. Okay, and this is a model that you obtain when you consider the limit of high rotation of a 3D flow. What you find in the limit of high rotation is that the flow is essentially two-dimensional. This is called the Taylor-Prudman Theorem. Okay, so it's two-dimensional and divergence-free. So it's given as the orthogonal gradient of a stream function, which is this one. And when you look at the asymptotic equation satisfied by the stream function, you under certain assumptions. So for instance, the rotation should not be exactly what I wrote yesterday. It's not just 1 over the Rossby number times the vertical, the rotation vector is just, it's not constant, it has to be linear. This is called the beta plane approximation. And under this assumption, this is the equation that you get for the stream function. Okay. Maybe one more word. Actually, this is the equation in vorticity form. Okay. because you know that the Laplacian of psi epsilon is the curl of u epsilon. Okay? So here, when you see the bi-Laplacian of psi epsilon, you need to think that actually this is the equation for the vorticity. Okay? Okay, so I won't say more about the derivation of this equation today, but let me just say that this is an equation that describes oceanic currents on a large scale. So omega is your ocean basin. Okay, x is the longitude and y is the latitude. So y is north to south, and this equation is valid both in the northern and in the southern hemisphere with the same signs. Okay, really the same equation. Okay, good. So now this is the equation that I will be working with, and so the first part of the talk will be dedicated to what is called geostrophic degeneracy. Okay. And so I'm going to explain a bit what the issue is. So, if you remember yesterday's talk, yesterday I told you that when you have an equation that is linear with constant coefficients near a flat boundary, you have a very robust method to compute, at least formally, the sizes of the boundary layer profiles using modal solutions. Okay? And that this method could apply in a number of cases. I didn't describe them all for a lack of time, but essentially, even for non-flat boundaries, you can use it using symbolic calculus tools and semi-classical analysis, as long as you are in a non-degenerate setting. A non-degenerate setting means that the size of the boundary layer that you find does not depend on the point of the boundary you're looking at in the phase space. Okay? And here, this is precisely what is going to fail. So let me explain. So if I follow, so first, this is typically a singular perturbation problem, okay? Because this is of order 4. If you look at the limit as epsilon goes to 0, you get an operator of order 1. So we are typically in the setting that I described yesterday. So formally, as epsilon goes to 0, you find that psi epsilon will converge. Okay, I'm going to put a weak arrow here because we can prove that actually the solution psi epsilon is bounded in L2, so you can pass to the weak limit. So psi epsilon converges towards some psi bar. It's not even formal, it's actually rigorous. And psi bar satisfies dx psi bar equals f. Okay. So obviously for this equation, you cannot enforce all the boundary conditions as the previous one. So it's always the same thing. It's a singular perturbation problem, so you lose part of the boundary conditions. This is why you have some boundary layers. But here it's not obvious a priori which boundary conditions you should take for psi bar, right? So essentially, if I draw a picture, so this would be my domain omega, and for psi bar, I'm saying that okay, if I'm at a given point, I need to integrate around a horizontal line like this. But I can choose to take psi bar equals 0 here, for instance, or there, but not both. Okay, if I assume that psi bar is 0 here, then I will integrate from here to here, and then the value here will just be the integral over this whole dashed line, and then psi bar won't be 0 at the other end of the interval, and vice versa. Okay, so I don't know which boundary condition should one take for psi bar. And to understand which boundary condition you should take for psi bar, actually, you need to perform the whole boundary layer analysis. So let's go. So to use the boundary layer analysis, it's nice to switch to local coordinates. So I'm going to introduce them right now. So let me zoom in on a part of the boundary. So this is my domain omega here. I will denote by S the arc length on the boundary. So this is S, and I orientate the boundary in the clockwise direction. So S is the arc length. And I will denote by Z the distance to the boundary. Okay, so this is Z. Okay, and one last notation. I will denote, so this is a right angle. I will denote by theta the angle between Ex, which is my the unit vector directed from west to east, and my normal. Okay. Okay, so since omega is smooth, if you are in a local tubular neighborhood of the boundary, a small neighborhood of the boundary, this is a good set of coordinates, and it's obviously adapted to boundary layers. Okay, so it's adapted to a local description of your solution, and in particular to no, it's the angle. Okay, so you can compute the Jacobian in these coordinates. I'm not going to write the whole Jacobian. So the Jacobian itself is not so bad. If you when you compute the bi-Laplacian, things get really messy. Okay, so I won't do that. But I'll just write down what dx is. So dx is, and I'll look at my notes because otherwise every time I get the sign wrong. So it's minus cosine theta dz plus sine theta over 1 plus z theta prime ds. Okay, so you can check that this is consistent. When the cosine of theta is equal to 0, then essentially, well, when you are when theta is equal to plus pi over 2, so you are your normal vector is just EY, and your dx is just ds, is the convention that I chose. Okay, and you can check also that when theta is equal to 0, so your normal is just ex. It's also everything is fine. Okay, and if I remember what I did yesterday, it's natural to look for a solution. Solution of dx pi epsilon minus this equals 0 in the form psi epsilon equals exponential of I ks minus lambda z times some phi epsilon. Okay, where so here k will be in z up to okay, I can always normalize things LZ. Okay, because you see S is periodic. Okay, the arc length. And lambda is has positive real part. And is very large. Okay, this is, so I denoted by k because so yesterday this is the variable that I denoted the psi prime actually. But here, so S is my arc length. But here, since it's something that is discrete, I denote it by k to remind you that it's actually it's your Fourier mode, okay? But it's more of a Fourier series than a Fourier transform. Okay, so this is what yesterday theory prompts me to do, and I plug that into the equation, and I try to find an equation for lambda. Yes. That's a good question. I think in yesterday's theory, I wanted to have a global solution, actually. But the point that I'm going to make is that this is not quite possible. And actually, you shouldn't look for a periodic solution. But let's say at this stage, I'm just trying to look for an equation for lambda. So I think one could argue that this is even though yesterday I was looking for global solutions, you can more or less localize everything. And even if you are only looking for a local solution in S, you still get the same equation for lambda. That's what I would say. I think yesterday in everything that I presented, everything was global. But even so, you can localize things in the phase space, and then you get something that is local in lambda. Yes, and actually, I will try to make a point that this is not a good approach. It's a good approach to try to guess what the sizes are, but in the end, my approximate solutions will not look like that. Okay, so now you plug this into your equation. You use the formula that you have for dx, which is written right there. For the bi-Laplacian, as I said, things are a bit horrible. Okay, but don't worry, because in the end, since lambda is very large, the only thing that matters when you compute the bi-Laplacian is just the fourth derivative with respect to z. This is the highest derivative. Okay, all the other ones are negligible. Okay, so when you do the same approach as yesterday, the equation for lambda that you get approximately at least is lambda cos sine theta plus I k sine theta minus epsilon lambda 4 equals 0. So actually it's not equals 0, it's almost equal to 0 because next to this lambda 4 there are other terms like k4 or things like that that I'm neglecting here. Okay, so this is my equation for the boundary layer sizes. Okay, again, just checking the signs. Yeah. Okay, so now see, the situation is a bit different from the ones that I presented yesterday because the lambda that I have here depends on theta, so it depends on S. Okay, because theta is theta of S, it moves along the boundary, obviously, and it also depends on K. Okay, so it really depends on the whole phase space. Okay, so now let's do the same thing as yesterday and try to find what the size of lambda is. So size of lambda and actually of the lambdas with which one? Well, yes and no. In the bi-Laplacian term, you have a dx, but you also have a dy. In the dy, you will have a sine theta dz, and the combination of the two will give you lambda 4. Another way to see this is, okay, S and Z are really Cartesian coordinates locally. Yeah, yeah. So S and Z are locally Cartesian coordinates. So the expression of the bilaplacian will be very bad, but at main order, if you say that only the z derivative counts when you're computing the bilaplacian, the highest term will be dz4. Okay, so when you look at this equation and you try to see what the size of lambda is, you see that there are different regimes depending on whether or not cosine of theta will be close to 0. Okay? So there is a first case when cosine of theta is far from 0, so bounded away from 0. Okay. And in that case, you see that this equation has 3 roots, which are of size epsilon to the minus 1/3. So let me call this BLE, that BLS for boundary layer size. Then the equation for the boundary layer size has 3. Maybe I can put some color into this. So 3 roots of size epsilon minus 1/3. So let me denote them as lambda equals epsilon to the minus 1/3 capital lambda. And the capital lambda will be given by lambda to the power 3 equals cosine theta. Okay? And so when you only need to keep the roots with positive real parts. So let me draw a picture, or 2 pictures actually. If cosine of theta is positive, then you will have 1 root right here and 2 here and here. Again, you need to have a bit of color so that you can see something. So you have 1 root there and 2 there. These 2 have negative real part, so you discard them. Okay, they don't correspond to boundary layers. So you have 1 root with positive real part, and so cosine theta, this is the east boundary. Cosine theta positive. So you have 1 root with positive real parts, and 2 roots with negative real parts. Okay? Okay, this is where the troubles begin. Okay, and then when cosine theta is negative, so this corresponds to the west boundary. Okay. Then the picture is the symmetric, and you have 1 root right there and 2 over there. So you have 2 roots with positive real part and 1 with negative real part that you discard. And 1 root with negative. Okay, so you see that there is a dissymmetry between the east and the west, which, and okay, I'll comment on that further later. Okay, but this dissymmetry precisely comes from this analysis, and so there are, so the equation has 4 roots. Here I have found 3 roots, each of size epsilon to the minus 1/3. Okay, and then there is 1 additional root, which is of size 1, which is just minus ik over minus ik tangent of theta. Okay, and actually this one corresponds to the interior flow, to the interior solution. Okay, it's not a boundary layer. It's the same as, you know, at the very end of yesterday's lecture. Sometimes I told you, okay, these roots that we find that are of size 1, they correspond to the incident or the reflected wave. Here it's the same thing. This root of size 1 corresponds actually to the interior flow. In A and B, yes. Yeah, you always find the three roots of size epsilon to the minus 1/3. It's just the sign of the real part that changes, and then there is always this root. Okay, so I'll finish the analysis with the second case, and then I'll comment on everything. The second case is the case when cosine of theta is very small, or possibly actually equal to 0. So, for instance, you can think of the case when omega has a stadium form. So when I write something like this, I'm not thinking of something very elaborate in terms of, I don't know, homeomorphisms or whatever. I'm just saying, okay, think of an omega that has the following shape, okay? Then you have a large portion of the boundary here where cosine theta is exactly equal to 0. Okay? It's not small, it's 0. Okay? So in that equation, you don't have a choice, you need to balance these two. Okay? The cosine theta cannot do anything for you. In that case, you find the 4 roots of size epsilon to the minus 1/4. Okay, so you have lambda, which is epsilon to the minus 1/4 times capital lambda, and lambda to the power 4 is equal to ik sine theta. Okay, and so then the exact picture will depend on the sign of this quantity. Okay, so you will have, but okay, the two cases are similar. You have either this is positive, and so the roots are these ones. So you will have, this is pi over 8. And then you just rotate them by pi over 2. We'll have one here, and one here. So this is the case when k sine theta positive, and otherwise the picture is not very good, but you get the spirit. It's like this. Okay, so this is 3 pi over 8. Okay, and this is in the case where k sine theta is negative. The important thing is that in both cases, you exactly find two roots with positive real part and two with negative real part. Okay, so you discard these two, and you keep this one, and you keep this one, and here you discard these two, and you keep these two. Okay, so you have two roots with positive real part and two roots with negative real part. Good. So now what does that teach us? Several things. So I'll make a bunch of comments. So the first comment is that you can lift two boundary conditions on the west boundary and on the north and south boundaries. Okay, so we can lift two boundary conditions everywhere except on the east boundary. Okay, that's good because you have exactly two boundary conditions to lift: the trace of psi and the trace of its normal derivative. So everywhere except on the east boundary, you will have 2 degrees of freedom, and you will be able to lift these two traces for the interior top. Okay? The only place where you cannot do that is on the east boundary. So this tells you that actually, in what I wrote over there at the very top, the boundary condition that you should take for psi bar is that psi bar vanishes on the eastern boundary. Okay? So one can lift two boundary conditions everywhere except on gamma E, which is the place where cosine theta is positive. So you need to take psi bar on gamma E equal to 0. Okay? So the boundary layer analysis is prescribing where the psi bar should vanish. The consequence of that is that, okay, if you look at your solution, so if you believe, at least formally, in this analysis and that you use it to construct an approximate solution for your equation, so your the approximate solution, so psi bar, psi epsilon, should behave like, say, psi epsilon equals psi bar plus something epsilon to the 1/3 psi east of SZ over epsilon to the 1/3 close to gamma E. Okay, so this one is designed to correct the trace of the normal derivative of that one. Okay, this one vanishes on gamma E, and this one has a small trace. And then to cancel out the normal derivative, this is what prescribes you the choice of this one. Okay, and it should behave like psi bar plus a linear combination of two, say, psi w plus or minus as z over epsilon to the 1/3 goes to gamma w. And here, these two are designed so that they cancel out both the trace and the normal derivative. Okay, I'm not doing the whole computation, but they're essentially the linear combination of exponentials. Okay. So this is what your approximate solution should look like in the vicinity of these two pieces of the boundary. And now remember that U epsilon is the orthogonal gradient of psi epsilon. Okay? So when you want to, so this is the stream function. The stream function itself is bounded. But if you want to look at the velocity, no? If you want to look at the velocity, then you need to take the orthogonal gradient of that quantity. And the thing is that when you take the orthogonal gradient of the first line, you will keep something that is bounded, say, in L infinity. But when you take the orthogonal gradient of the second line, you see that you have an epsilon to the minus 1/3, which pops out. Okay, and so the velocity in the vicinity of the western boundary is unbounded. Okay, so let me write that down. Maybe I'll keep the model. So as a consequence, one expects that U epsilon is further one in an infinity close to gamma E. And U epsilon is a further epsilon to the minus 1/3, so it's very large in an infinity close to gamma with mass. And this phenomenon is precisely what is called the Western intensification of currents. Okay, and as I said, it's responsible for the birth of a number of oceanic currents, such as the Gulf Stream, Kuroshio currents, etc. Okay. In this one, well, because so close to the western boundary, the trace of this quantity is 0. Okay, this is how I choose psi bar. Okay, but close to the western boundary, the trace of that quantity is not 0. It's just the integral over my whole dashed line over there. Okay, so it has a non-zero trace, and I need to compensate for it with my two boundary layer profiles. Okay, so these two boundary layer profiles will have amplitude 1. Okay, so that's why you have an epsilon to the 1/3 here, because this quantity vanishes on the western boundary, but no epsilon to the 1/3 here, because this quantity does not vanish on the western boundary. Okay. No, I'm not dropping it, just to recall that the yes, for the normal derivative. Yes, it is 0 at the boundary. So this one will be small close to gamma E. But yeah. Okay. So you expect the currents to be much stronger close to the western boundary. Okay, and this is really important. An important fact in oceanographic models. Maybe I can give some references at this stage. So if you're interested in learning, I would say, many facts about physical oceanography, I think a good reference is the book by Pedlowski. It has really been a source of inspiration for mathematicians throughout the years, I would say. It has led to a number of mathematical studies, but I think if you want to learn a lot of the things that I said, it's really a good reference. And then for the mathematical analysis, this is present. This is done in a paper by Desjardins and Grenier. And at the linear level, and then it has been extended to a number of situations. So there is so I won't cite everybody, but there is a paper, for instance, by Brecht and Gérard Varret. And what I will be talking about next, and dealing in particular with the degeneracy that I haven't spoken about yet, this is something that we did with Laure Saint-Raymond. Okay. Good. So this was the first part of the comments that where you should take the condition for a psi bar, Western current intensification. And now let me go to the degeneracy part. So you see that here you find two different. Is there a? Okay. Not exactly what I wanted, but fine. So here you remember that my condition for non-degeneracy was that the power I found for the boundary layer sizes should not depend on the frequency, okay, or on the portion of the boundary that you're considering. Let's say on your point in the phase space. Here, this is precisely a situation where this doesn't occur, because you find that when you are close to the eastern or western boundary, your power is -1/3. And then when you are close to the southern and northern boundary, it becomes -1/4. Okay? So this is really I think one of the simplest case that I know of degeneracy. Okay? And so typically, this is a situation in which you cannot apply as a black box, I would say, the theory that I presented yesterday. Okay. Ouais. Yes. Yes, there's also. Yes, that is correct. Yeah, so the last point that I wanted to make, so number 3, is this is a degenerate case. Because you have 1/3, so say with the notations that I had yesterday, you have Q equal -1/3 close to or on gamma west and gamma E, and Q equals -1/4 on gamma north and gamma south. Okay, I haven't introduced all the notation, but you can guess what it is. Okay, and so the next question is, how can one construct an approximate solution? Okay, so why? Okay, so why do you want to construct an approximate solution? I would say there are several reasons. First, if you are a mathematician, in the end, you want to do a theorem. Okay, so this is what your job is somehow. So okay, this is all very nice, but you want to be on firm ground and to prove that actually this formal theory is giving you the truth somehow. I don't know, but that you want to have some rigorous derivation of this, okay, or a rigorous proof of this, okay. And to do that, I know actually no other way than plugging this ansatz into what I would call an approximate solution, and then proving that the difference between the actual solution and your approximate one is small in some suitable sense. Okay? So yeah, I would say that the purpose of constructing an approximate solution is actually to check that you are not completely mistaken through this formal analysis. Okay? Okay, so if you believe that, I would say, in the analysis that I presented yesterday, the first attempt is to write psi epsilon, or you take a psi epsilon app, say, as, okay, your interior term psi bar, which vanishes on gamma e, and then you're going to take a sum for k in L, Z, of, let's say, some, I'm going to take some coefficients, and I will take a sum over all possible, okay, I'm going to take a sum over plus and minus to account for the fact that on most pieces of the boundary I have two boundary layers, so of A plus and minus of K, and I will take AKS minus lambda plus or minus Z, okay, where the lambda plus and minus are the ones that solve this equation. Okay, so you can, the first thing that you can try is something like that. Okay, you compute A plus and minus of K so that the trace on the boundary vanishes and so on. And so at first with Laure Saint-Raymond, we tried to do something like that. And the problem is that it really doesn't work. So this fails. Yes, so exactly. So lambda plus and minus, they are functions of K and S, obviously. Because actually, at main order, there's something like epsilon, at least on the east and west boundary, there are epsilon to the 1/3, sorry, there are cosine theta over epsilon, everything to the 1/3. Okay, so let me write this down. They're like cosine theta over epsilon to the 1/3 plus some factor on the east boundary. Yeah, exactly. That's the issue. So this fails. And my understanding, so we tried really for quite a bit to make that work, and every time it completely failed. And my understanding of the computation, so it was a while ago, but still I remember a little bit. But actually, the lambdas change in a very abrupt fashion when cosine theta goes to 0. Okay, they change really very rapidly. And I think this ansatz is just too singular in the end. Okay, it introduces like some kind of artificial singularity within your solution that isn't really there. Okay, so the change in lambda is too abrupt. Okay. So I would, and this is really linked to the degeneracy issue. Okay, if you didn't have a degenerate situation, then you wouldn't have such an abrupt change in lambda, and essentially this would work. Okay, here this really the fact that this ansatz fails is really linked to degeneracy. Okay, so you need to do something else. So you step back a bit from this formula, okay? Because like I said, this doesn't work, and so we and you go back to the formal analysis. The formal analysis is telling you, I think it's again here, yes, that when you are close to these flat portions of the boundary, then your lambda should be exactly 1/4, epsilon to the minus 1/4. Okay. And so you say, okay, first I'm going to try to understand what happens on this portion of the boundary. Okay, let's assume that my domain omega is actually a stadium. Okay, and let's see what happens for the solution in the vicinity of it. Okay? So in the vicinity, okay, so I'm going to choose a convention. Okay. So it's the vicinity of gamma S, so it's the southern portion of the boundary. You look for psi epsilon in the form psi epsilon equals psi bar plus some function which I will denote by psi s of so s and z over epsilon to the 1/4. Okay, so again, I have a very flat portion of the boundary that looks like this. So this is my domain omega, and this is gamma s. Okay. Now you plug this into your equation. Ah, no. Okay, so you plug into the equation and into this one, and what you get is the following equation for gamma s. You get ds of psi for psi s. Sorry. I'm putting a little bars here because this S is not the same as this one, okay? I had to choose between north and south. The problem is that if I'm looking at things close to the northern boundary, then I would have a backwards equation. I wanted to avoid that. So that's the reason why I chose this, but it's not a perfect minus D, and I will denote this by, let's say, capital Z to the power 4 psi S equals 0. Okay, so this is my equation for psi s close to the southern boundary. And in fact, it's a perfectly nice equation. Okay, it's a diffusion-like equation. You have a bi-Laplacian instead of a Laplacian, but otherwise it's just like the heat equation. You can endow this equation with two boundary conditions. Okay, so you can assume that this psi s at point capital Z equals 0 is minus psi bar at this point, and that the normal derivative cancels out the normal derivative, but so there is an additional epsilon to the 1/4 factor. Okay, so this is a well-posed equation. The well-posed diffusion equation, okay, it's heat-like. Okay, so you need to endow it with an initial data, actually. And something that we found quite beautiful with Laure is the fact that you need to prescribe the initial data is prescribed on the east end of the interval. So it's exactly the same as what happens for the interior term. Okay, you construct your whole solution from east to west. Always integrate from the east, starting from the east boundary, going to the west, okay? And so for the initial data, you prescribe it on the east end of the interval. And so actually you just take psi capital S at point S equals S naught. I don't know if I forgot to, this is equal to 0. So my S naught okay, so this is S naught, this will be some S1, and let me remind you that S goes up. Okay, so you prescribe an initial data for this evolution equation on the east end of the interval, and then you just solve the equation with two boundary conditions. Okay, so at least locally, you know what you need to do for the south and the north boundary layers. And then the last question is, how do you patch everything together? Obviously. Okay, because I was telling you, this is the main issue when you use the previous ansatz. It fails because you have abrupt transitions, and you're going to tell me, yes, but here you didn't handle the transition at all. Okay, you construct things separately on every piece of the boundary. You still need to patch everything. Okay, so that's actually indeed a difficult. So this is quite a technical part, and so I won't go too much into it, but I will tell you the idea. Okay, and so the question is, how do you patch everything together? On the eastern boundary, yes. So on the western and eastern boundary, you can do things completely locally. Meaning, yes. Yes, exactly. The issue is really the transition between different portions of the boundary.
So you don't need to do this.
No. Yes. Yes, you can. And actually, people, so for instance, in these two papers, there is an assumption on F that F vanishes identically close to the northern and southern extremities of the domain, so that you don't need to look at what happens on the northern and southern boundaries. Okay? And in that case, you can use that analysis, because somehow you get rid of that degeneracy by just assuming that everything vanishes in the degenerate region. So to patch everything together, well, you can notice that the equation is linear. Okay, so you can use a superposition principle. And more precisely, you use a partition of unity. Sorry. So you write 1 as the sum of 4 smooth functions. So phi w of s plus phi n of s plus phi e of s plus phi capital S of s. Okay, so each phi I of s is smooth, compactly supported. Phi I of s is almost the indicator function of gamma I. Okay, but not quite. There is a bit of it's a bit smoothed out, and it depends on epsilon in a way that I would not describe. Okay, you need to construct this by hand. Really. Okay. Okay, and then what you do is that you construct each boundary layer by lifting the maybe, I don't know if phi is a good, maybe let me call this chi. It would be less confusing with the stream function. Sorry. Okay, and then you construct every every boundary layer profile close to every boundary by by enforcing that psi BL I at the point z equals 0 is equal to minus the psi bar. So that's for I equal everything but the west part. Okay. And in every case, you have dz psi BLI z equals 0 equals minus ki lambda I minus 1 dn psi bar. So that's for everybody. Okay, so I'm not going too much into details here. I know that this is a bit sketchy. But the idea is really this, that once you understand, let's say, every piece of the puzzle, you put everything together by playing on the amplitudes. And that's important, of the boundary layers, and not on their sizes. Okay, you do not try to connect the sizes. This is really, really, really important. To connect the different sizes of the boundary layers. Because when you use the previous ansatz, which failed, my understanding is that you try to connect the sizes together, the sizes of the different boundary layers. Okay? And when you do that, this is precisely what is creating these strong singularities. And you should avoid to do that. Every time you have I would say you need to avoid to do that every time you have a degenerate situation. When you have a degenerate situation, I think what happens is that you have a coexistence of different boundary layers, of different sizes, and you shouldn't try to connect the sizes. But you can take a superposition of different boundary layers with different amplitudes. Okay, so you somehow, when you do that, you connect the amplitudes through this partition of unity, but you don't connect the sizes. And this is much, much less singular. Okay? Okay, so I'm being a bit too chatty and already a bit, I don't have that much time to talk to you about rough boundaries. So I'll just check that I haven't forgotten anything too important. Okay, let me just, I'm not sure I'm going to write down, well, maybe I can write a theorem, but just a very, in a very abstract way. And so in the end, the theorem is that you have psi epsilon minus psi up in a certain norm. So actually, it's the H2 norm, but I'll write it in this way nevertheless. Is small. So why am I writing it like this? The important thing is that here things are so singular somehow that you don't always prove that the difference is small. But actually, you don't care. This is not what is important. When you want to prove that your approximate solution is legitimate, you just want to prove that the difference between your true solution and the approximate one is smaller than the size of the approximate solution. Okay? this is what is justifying your asymptotic expansion in the first place. Okay, so you need to pick a functional space such that you, or to pick or to push your expansion sufficiently far, whatever, so that you have that type of theorem. But in such situations, when you have a singular perturbation problem, quite often you cannot prove that your remainder is small. But again, this is not a problem. Okay? This is a typical. This is what you should aim for. Okay, so are there questions? Oui. Well, so you have, well, yes and no. So psi bar handles the f, and then you have a remainder which will be epsilon by Laplacian of psi bar. Yes, but that is small. So typically you can treat that in a perturbative fashion. As long as f is smooth and everything, typically that's the type of thing that we put in the right-hand side. Okay. So just to conclude, sorry.
Just try something. I'm not sure if you agree with me or not. I believe what's happening on the west boundary is an accumulation of cross viewers.
An accumulation of what? Sorry.
Cross viewers.
Ah. I'm not entirely sure, in the sense that this is a purely stationary setting.
Yeah, but this is a setting. Comes from the real world.
Yes.
This cross viewers.
Yes. No. Yeah. Yeah. Okay. Yes. Yeah. Yes.
But what's missing here? You are missing Kelvin. Cross viewers. Hit the west. You will Kelvin west.
Well, I'm not sure.
It's missing in the setting. You have
No, but okay. So maybe I can. You can add a time derivative, and this doesn't change the analysis. Actually, it makes things a little easier because, at least mathematically speaking, when you have an evolution equation, somehow you get for free an L2 bound. Okay. Which you don't have here. You have to work a little bit to have this L2 bound in your equation. It's not very hard, but still. So adding a time derivative here doesn't change the whole analysis. Yeah, I see what you mean. No, well, for sure this is only part of the picture, and then obviously you have a counterflow. Yes, that's true. But it's still a part of the picture. I don't think it's. Yeah.
The artifact is not the real world. You run into problems.
I'm not sure. I think you run into problems because problems are there. Yeah, exactly. I think you run into. I think it's legitimate that you run into these problems. And so maybe one thing that I can add. So here I explained everything in the case of a simply connected domain and so on. But you can do exactly the same for a general domain with islands. Okay, and then actually, if you have islands like this, then here you have some discontinuity lines in your psi bar, and these dashed lines behave exactly as the northern and southern boundaries. Okay, so you expect to have a discontinuity here and here in your solution, and a kind of boundary layer discontinuity, and so some strong currents here, and this is actually what you observe. So I think this is not, okay, it's an idealized model for sure, but I think that the issues that you encounter are there. I don't think it's because you forgot something in the model. I think they should be there. But yeah, I'm not sure it's I'm not sure it's an artificial difficulty to say that. I think it's an actual singularity in your equation. Yes, but that somehow reflects something in the real world. No, yeah, sure, it's idealized. Yeah, okay. No, I agree, but yeah. So still you can add a bunch of things back into that equation. So for instance, you can add the part that comes from the Ekman pumping, and this doesn't change anything to what I just said. What I don't know is what happens to this analysis when you add back the nonlinear term. To my knowledge, this hasn't been done yet. And actually, I have no idea what happens when you plug the convection term back in. Okay, so I think this is it's a difficult question, and I don't know how to address it. Okay. Yes. No. I was thinking, I think, more in mathematical terms, like justifying. I don't know how much of it you can extend. The construction that we do is really extremely linear, and for instance, if you add in a nonlinear term, it's possible that it has some importance close to the western part of the boundary, but not the northern part, and then you need to understand what's going on. It's not so obvious. So that's what I meant. Okay, so I don't have much time left, but still I'm going to talk a little bit what happens in the case of rough boundaries. Just to give you an idea that what we did can be generalized to cases where the boundary is not flat or not smooth. So now I'm taking omega to be actually some omega epsilon. So it's the same equation as before. And there's something I forgot to say that I need to say afterwards. And this omega epsilon, okay, I'm going to take it in the following way. So it will be the set of xy in R2, such that you have minus or plus epsilon to the 1/3 gamma of y epsilon to the 1/3 smaller than x smaller than 1, and y between 0 and 1. I'm going to draw a picture. So it has the following form. So it's something wiggly like that. Okay. So again, it's very idealized. The goal. So this is my boundary x equals epsilon to the 1/3 gamma of y epsilon to the 1/3. Okay. So the goal is to study the influence of, let's say, rough coast. Okay. And so here, for the sake of the presentation, I took something that is very simplified, so flat boundaries everywhere except on this one. And here, a perturbation of a flat boundary, but you can do something that is much more general. Okay, you can have curved boundaries everywhere. You can take a perturbation of a curved boundary and so on. Okay. The important thing here is the scaling. You see that I chose this power epsilon to the 1/3 because this is the size of the boundary layer on the west coast. Okay, so it's not by chance that I took. Okay, and I choose the same scaling in x and y, so that they would actually have the same importance in the bilaplacian. Okay. Okay, and to avoid all the issues that I just mentioned about on the close to the northern and southern boundaries, I'm assuming that the support of f, that there exists some delta which is positive, such that the support of f is included in the set where delta is between y is between delta and 1 minus delta. Okay, so nothing happens close to the northern and southern boundary. So no south north boundary. Okay, so in that case, one last thing here is that gamma is a general function, let's say W2 infinity, okay, of R, but I'm not assuming anything on its structure, and for instance, I'm not assuming that it's periodic or anything. Okay, and then the question is, okay, how do you handle such situations? Well, so the issue is really to understand what happens close to the western boundary, because inside the domain you still expect to have psi that behaves like psi bar, which will be given by the same formula as before. So it's of dx psi bar equals f and psi bar equals 0 on this eastern boundary. So now the question is the equation for psi BLW. Okay, so you still expect the size of the boundary, the west boundary layer, to be epsilon to the 1/3, but now because of this small scale structure in the western boundary, you expect also the western boundary layer to have a small scale dependency in y. Okay, so the ansatz is that psi epsilon behaves like psi bar plus some psi w of x over epsilon to the 1/3, y epsilon to the 1/3, and y goes to gamma w epsilon. Okay, so you plug that into the equation. And what you get is the following. So let me denote this fast variable capital X and this one capital Y. So you obtain dx psi w minus the bilaplacian with respect to x and y of psi w equals 0 in a domain that I will call omega BL. And psi w on the boundary of omega BL is equal to minus psi bar at x equals 0, and dx psi w on the boundary of omega BL equals minus gradient of psi bar at x equals 0 times the normal. It's the n, sorry. And so let me just write down what omega BL is. Omega BL is the set of points in R2 such that x is bigger than gamma of y. Okay, so it's a Now it's on scale 1, but it's a bumped half space. Okay, it's everything on the right. Okay, so it's a nice elliptic equation, but it's set in an unbounded domain in all directions. Okay, and the issue, there are several issues. The fact that it's unbounded in the normal direction to the boundaries makes for the fact that you don't have a Poincaré inequality. And the fact that it's unbounded in this direction, plus that you don't have any decay with respect to y, makes you look for solutions that have infinite energy. Okay, so the difficulties from the fact that omega BL is unbounded in y, and you have a lack of decay. Is unbounded in all directions, actually, and you have a lack of decay in y. Okay, so maybe I'll keep a bit of time tomorrow to finish telling you about how you handle such cases, but maybe I'll just give you a very, very, very short preview. So to deal with the unboundedness in y, the idea is to decompose your domain into two parts. So unboundedness in y, you domain decomposition. Okay, so you have your domain omega BL, which is like this, and you introduce an artificial boundary right there, far from the bumps. Okay. This idea was introduced by David Gerard-Varret and Nader Maspoudi for the Stokes system. It's also an idea that is used quite frequently in numerics to work with a bounded domain. Okay, and so the idea is to use a transparent boundary condition on this dashed line. Okay. Yes. Yes, unbounded syntax. Thank you. Sorry. So you use the domain decomposition. So the idea is that here, since your domain, the boundary of your domain is flat, it's amenable to Fourier analysis. Okay, so you can write everything in Fourier terms, and then you write a transparent boundary condition on this dashed line. And then you're back to working with a domain that is bounded in X, but with a transparent boundary condition on this dashed line. So this is what I will explain till tomorrow at the beginning of the lecture. And then to deal with the unboundedness in Y and the fact that you have functions which with infinite energy, you need to use some specific energy estimates. So actually, the estimates we use go back to Lalizhenskaya and Solonikov, but I will present maybe a very simple form by just performing weight estimates with a weight and proving that you can, even though you have functions of infinite energy, you still can perform some energy estimates in a rather classical way. Okay, so again, I'll stop here for today. I'll use maybe 15 to 20 minutes of tomorrow's lecture to finish what I had to say about this problem, and then for the rest of tomorrow's lecture, I will talk about the Prandtl system. Thank you.